Hello guys, in this video we will discuss about the diagonalization of a matrix, and we will discuss some of its properties or some conditions under which a square matrix is diagonalizable. So before going to start those conditions, first let me give you some tools which will be used for those conditions. So let us start with the algebraic multiplicity of an eigenvalue. So algebraic multiplicity of an eigenvalue lambda of a square matrix A of order n is a number of times lambda occur as a factor of the characteristic equation. What does it mean? Suppose you have a square matrix A of order n cross n. If you find out its characteristic equation, you know that it is given by determinant A minus lambda I equals to 0. For example, suppose this is lambda 1 minus A, lambda 1 minus B, lambda 1 minus lambda 1, lambda 2, lambda 3 minus C, and so on is equal to 0. Suppose this is power R, this is power S, this is power T. So this is basically your characteristic equation where R, S, and T are some positive numbers. Uh, so algebraic multiplicity means what? You see that you have eigenvalues A, B, and C for this matrix according to this characteristic equation. So if you see that this factor is appearing R times, so it means the algebraic multiplicity of the eigenvalue A is R. Similarly, for eigenvalue B, it is appearing S times in the characteristic equation as a factor. So algebraic multiplicity of the eigenvalue B is S, and for C it is T. Second thing is geometric multiplicity. Geometric multiplicity of an eigenvalue lambda is nothing but the dimension the dimension of eigenspace of lambda, or you can say in easy words that the number of linearly independent eigenvectors corresponding to the eigenvalue lambda is called as the geometric multiplicity of lambda, or number of linearly independent eigenvectors corresponding to lambda. For example, suppose you have lambda is equal to A, B, and C. Suppose these are eigenvalues of a square matrix A. Now suppose corresponding to A, if you have two eigenvectors, then we will say that the geometric multiplicity of the eigenvalue A is 2. That means just you have to see how many eigenvectors corresponding to the eigenvalues of the matrix. So that is called as the geometric multiplicity. One more thing as a remark, always remember that the geometric multiplicity of an eigenvalue lambda is always strictly less than or equal to the algebraic multiplicity of that eigenvalue. One more point, if lambda is an eigenvalue of algebraic multiplicity M of a square matrix A of order n, then the number of linearly independent eigenvectors associated with lambda is given by the formula P is equal to n minus r, where r is what? R is the rank of the matrix A minus lambda I, and the value of P will always be lies between 1 and m. That means minimum it can be 1 and maximum it can be m. That means the equal to its algebraic multiplicity. So this remark says that if you have a square matrix A of order n whose eigenvalue lambda having algebraic multiplicity as m have number of linearly independent eigenvectors as n minus r, where r is what? R is the rank of the matrix A minus lambda I. That means the eigenvalue lambda corresponding to which you have to find eigenvectors, just put here and you can find the rank. So let me recall you what is rank of a matrix. Rank of a matrix is nothing but the number of non-zero rows in the matrix after reducing that matrix into the row echelon form. Now we will discuss the conditions for a matrix to be diagonalizable. These conditions are the equivalent conditions. That means you can derive the one condition from the other condition. Suppose you have a square matrix A of order n, then this matrix will be diagonalizable if. So first point is this matrix has n distinct eigenvalues. Second point is it has n linearly independent eigenvectors. Third point is the sum of geometric multiplicities of the eigenvalues is n. And the last point, for each eigenvalue, the algebraic multiplicity is same as geometric multiplicity. If any one of these points is satisfied by a matrix, then we can say that the matrix is a diagonalizable, and all these points you can say are equivalent or they are just implying each other. So for example, you can see here that if you have n distinct eigenvalues, then it will have n linearly independent eigenvectors. Okay. Somehow, suppose you have a square matrix A of order 3. Suppose it has two eigenvalues, 1 and 4, repeated 2 times. That means the algebraic multiplicity of 4 is 2. So, in this case, if suppose corresponding to 4, you have two eigenvectors, and corresponding to 1, if you have definitely you will have one eigenvector, then in total you will have three eigenvectors, so it will be diagonalizable. That means if you have a matrix which do not have n distinct eigenvalues, but still you can get n linearly independent eigenvectors. That's why it is mentioning as a separate point. Third point is sum of geometric multiplicities of the eigenvalues is n. It means what? Suppose you have two eigenvalues. For example, here you have two eigenvalues, but corresponding to this 4, you have suppose two eigenvectors and one eigenvector corresponding to 1. That means in total you have three eigenvectors. So again, that means you can say that B and C, they are again saying the same thing. That's why I told you that these are equivalent points. Or the fourth point says that for each eigenvalue lambda, if the algebraic multiplicity is same as the geometric multiplicity, then the matrix will be diagonalizable. For example, again in this case, because the characteristic equation is this. So according to this point, if corresponding to one eigenvalue, if we have one eigenvector, and corresponding to 4 if you have two eigenvector, because the algebraic multiplicity of 4 is 2. So if they are same, then the given matrix will be diagonalizable. So I hope that these 4 points will helps you to identify that a matrix is diagonalizable or not. Now let us see an example. Check whether the matrix A given by this 1 2 2 0 2 1 minus 1 2 2 is diagonalizable or not. So as we already discussed four conditions, so you can check any one of the condition. Okay, so for this, for checking the diagonalizability of a matrix, first we have to write down its characteristic equation. So the for the characteristic equation of a matrix, you can visit this video in which you can get how I am writing down the characteristic equation of the matrix. So this is given by determinant A minus lambda I is equal to 0. So we will obtain this as lambda cube minus 5 lambda square plus 8 lambda minus 4 is equal to 0. If you factorize it, you will get lambda minus 1, lambda minus 2 square is equal to 0. So you can see here that the eigenvalue algebraic multiplicity of eigenvalue 1 is, you see that power is 1, and algebraic multiplicity of eigenvalue 2 is, you see here, power is 2. That means algebraic multiplicity is 2. So for the diagonalization, we will check that we will have three linearly independent eigenvectors or not. So we know that for corresponding to 1, we will get 1. So we will work for this eigenvalue 2. That this eigenvalue 2 has two linearly independent eigenvectors or not. So we will try to find out the rank of the matrix because we are going to use the result that number of linearly independent eigenvectors of an eigenvalue lambda with multiplicity m of a square matrix A of order n is given by P is equal to n minus r. N is the order of the matrix and r is what? It is the rank of the matrix A minus lambda I. So we will find out the value of the rank of the matrix A minus 2i because lambda is equal to 2. A minus 2i, how you will obtain? Just in the given matrix, in the main diagonal entries, just put minus lambda means minus 2. So you will have the matrix 1 minus 2, 2, 2, 0, 2 minus 2, 1, minus 1, 2, 2 minus 2. So this will be equal to minus 1, 2, 2, 0, 0, 1, minus 1, 2, 0. Just you can subtract, or you can rewrite this matrix as minus 1, 2, 2, minus 1, 2, 0, 0, 0, 1. Or if you just use the row operations in this matrix, basically we are reducing it into the row echelon form. So just subtract it, minus 1 minus it will be 0, 2 minus 2 it will be 0, and 0 minus 2 it will be minus 2, 0, 0, 1. So you can see here these two rows, you can rewrite this as minus 1, 2, 2, 0, 0, minus 2, 0, 0, 0. Now this matrix is in row echelon form, and if you see that we have two non-zero rows, so it means a rank of this matrix A minus 2i is 2. So number of linearly independent eigenvectors corresponding to 2 is n minus r. N is the size of the matrix. It is a 3 by 3 matrix. That means you have n as 3, r is 2. So you will have one linearly independent eigenvector corresponding to this eigenvalue 2. So corresponding to the eigenvalue 1, we have one eigenvector, and corresponding to eigenvalue 2, again we have one eigenvector. So in total, we will have two linearly independent eigenvectors for this matrix. So that means this matrix is not diagonalizable, because this is a matrix of order 3 and we do not have three linearly independent eigenvectors.